Minerals are the building blocks of the Earth, but did you know that minerals themselves are commonly made of shared building blocks? We can visualize the crystal structures of these minerals using a series of 3D printed building blocks called TotBlocks. In this video, we'll explore the 2-to-1 phyllosilicate minerals, and we'll use TotBlocks to construct their crystal structures. The crystal structure of the 2-to-1 phyllosilicates consists of 2 T modules for every O module, hence the numbers 2 and 1 in the name. The prefix philo means leaf in Greek, alluding to the infinite sheet-like structure of the T and O modules. TOT modules can be extracted from this arrangement to construct the other modular rock-forming minerals, making it the prototype structure for TotBlocks. The 2-to-1 phyllosilicates include minerals such as the biotite series and muscovite, which are both micas, as well as other minerals such as talc and porphyllite. The sheet-like structure of many of these minerals makes them useful in everyday life. For example, micas are commonly used in cosmetics to produce a glittery look, and talc is better known for its use in baby powder. So let's see how to construct these mineral structures. Here's the crystal structure of the mica group, which is the most important group within the 2-to-1 phyllosilicates. The structure consists of infinite sheets of TOT modules. Now we'll take it apart. To learn how to build the component TOT modules of this structure, take a look at the Assembly of TotBlocks video in this series. To build the 2-to-1 phyllosilicate structure, connect 2 sets of double chain width TOT modules such that there is no offset between the modules. There will be sites missing between the linked double chain modules where single octahedron pieces can be added. To vertically stack the sheets, vertical pegs are inserted into the slots of the O layer to form the connection. We can already begin to see the infinite sheets that we mentioned earlier. When we scale this crystal structure to the macro level, several key features of this mineral group emerge. When 2-to-1 phyllosilicates grow, they preferentially form along the strongest bonds in the structure, which would be the horizontal T to T and O to O linkages. The vertical bonds between the individual TOT sheets are much weaker. So, these mineral layers want to grow along the same plane, leading to a plating habit at the macro level. These vertical bonds between the TOT sheets don't just influence how 2-to-1 phyllosilicates grow. The bonds also influence how the minerals break. This dominant plane of weakness between the TOT sheets defines the basal cleavage plane that is characteristic of this mineral structure. The characteristics that we most commonly use to recognize micas and other 2-to-1 phyllosilicates are intrinsically linked to their crystal structures. For the mica structure, or the 2-to-1 phyllosilicates, silicon and aluminum will fit into the T sites. whereas magnesium, iron, and aluminum can fit into the octahedral sites. There's also an interlayer where cations can fit, such as potassium, calcium, and sodium, and also water. In this video, we've learned about the 2-to-1 phyllosilicates and how their structure at the atomic scale, that is, their infinite sheets of TOT modules, influences their macroscopic mineral properties. In particular, the weak vertical bonds lead to platy habits and a perfect basal cleavage. The crystal structure of the 2-to-1 phyllosilicates can be thought of as a protostructure for rock-forming minerals that are made of T and O modules, and these can be constructed using TotBlocks. We will explore these minerals in other videos.